relations as well as an investigation of something called first differences. So a linear relation is a relation when a graph forms a straight line. A nonlinear relation is a relation when the graph does not form a straight line. Pretty straightforward. Straightforward. Recall, for example 1, in the city, 50 kilometers per hour. 50 kilometers per hour. Kilometers per hour. Keep that in mind. Is a safe driving distance. Make a table of values from time 0 to 5. So remember, when we create our table of values, we get to pick all of these numbers in the X column. So if the person hasn't started driving yet, how far have they gone? 0. After 1 hour, if they're driving 50 kilometers per hour, they've gone 50 kilometers. At 2 hours, they've gone 100 kilometers. At 3 hours, they've gone 150. At 4 hours, they've gone 200. And at 5 hours, 250. It says graph the relation below, label the axes, scale the graph appropriately. So again, guys, making sure that you are scaling properly. We've got our X here. And we've got our Y. And I am going to do short form. This is distance. You would probably write out distance in kilometers. And this is time in hours. So we need to scale this properly. So time, so you can scale every other one just to spread your graph out. You don't have to, but I'm going to. And 5. So notice when I scaled by 1, I didn't put my 1 here. I said it's by half an hour. So this would be my first 30, then I put my 1. So some of you are making that error where you would put 1 here, skip 2, and then write 2 here. So remember, it's got to be scaled appropriately throughout the entire graph. And on this axis, we go up to 250. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 lines. So you can pick an appropriate scale. I'll probably go up by 25. So this is 50, 100. This one would be 150. This one would be 200. Whoops. Smiley face. And then 250. So if we're graphing at 0, 0, we've got a point. And remember, in a previous lesson, I said you really only need 2 points to graph. So I am going to graph 2 and 100. And if I'm using a straight edge and graphing directly through these points, everything else on your graph should line up nicely. Okay, so make sure you're using your straight line and you've got a graph that looks something like this. So this says write an equation for this situation. So we are always writing equations in the form of y equals mx plus b. So what is our rate of change? Oh, you remembered. We go back up to this 50 kilometers per hour. That would be our rate of change. And then what is our y-intercept? It's right. We don't have one. It's 0. It touches at the origin. So this equation is complete. Y equals 50x. Now consider the following equation. Y equals x squared plus 1. So again, I'm going to fill in my y values. Oops, not 23. And then remember what I did last time. I'm only going to do one example this time. Otherwise, you can go back and watch 2 videos ago how to do this. So you take your x value and you literally replace, oh shoot, the x. Now you know why I'm only doing it one time. And then you solve. 0 squared is 0, plus 1 is 1. So that means you get a 1 here. 1 squared is 1, plus 1 is 2. 2 squared is 4, plus 1 is 5. 3 squared is 9, plus 1 is 10. 4 squared is 16, plus 1 is 17. So if we scale this, and I really want you to do it properly, but for the purposes of this video, it is going to look something like this. And you're going to just take off like that. If you went negative numbers, it's going to be the same on this side and just take off upwards. So 1 is linear, 1 is non-linear. So it says compare the 2 examples above and state the differences that you notice. So linear equations from the table, they go up, your y values go up by regular intervals. The graph forms a straight line, and the equation is in the form for linear relations. So if this is only for linear relations, y values increase at regular intervals, the graph forms a straight line, the equation is in the form y equals mx plus b. If you're looking at nonlinear relations, the y values do not increase at regular intervals, they do not form straight lines on graphs, and they generally have exponents on their variables. So, or the variable is an exponent other than 1. Those are the differences between linear and nonlinear relationships. Let's look at first differences now. So Steve works in an auto shop. He receives a base salary of $30 per day and is also paid $5 for every car he washes. Complete the table of values. So 0 cars, 1 car, 2 car, 3 car, 4 car, 5 car. These are the ones you get to make up. His earnings. If he does not wash a car, how much does he get paid a day? $30, correct. If he washes 1 car, he gets $35. If he washes 2 cars, he gets his base pay plus $10. And you can see how this graph is increasing by 5s. So here it says write an equation that represents his earnings per day. So this would be our x column. This would be our y column, with the number of cars he washes. So remember, our equations our equations are always in the form of y equals mx plus b. This is lowercase y. So we're going to replace y with our earnings because this is what it's telling us in the question. Our slope is what he is paid per wash, $5 per wash. And his initial value, so when our x is 0, our y value is 30. So part C says calculate the differences between successive earnings. So one way to do this, or the easiest way to do this, is to start from the bottom. So here we're going to say 55 minus 50, and that gives us a difference of 5. Then we're going to go up 1 and say 50 minus 45. That gives us a difference of 5. 45 minus 40, gives us a difference of 5. So we're taking the bottom number, subtracting it from the one above. Then we take the bottom number here, subtract it from the one above. Then we take the bottom number here, subtract it from 40. So our next one is 40 take away 35 to give us 5. And lastly, 35 minus 30 gives us 5. So the first differences are 5. So what do you notice about first differences? I'm not going to do D. We're just going to look at first differences, and what do you notice about first differences? Hopefully that you notice that it's all the same. So if it's all the same, if the first differences are all the same, you have a linear relationship. So you can tell first by a table of values, if you look at first differences, your relationship is linear. So if I give you a table of values and I say, based on this table of values, determine if the relationship is linear. So you automatically should go, I'm going to check the first differences, because if they are all the same, then that relationship is linear. The first differences are also the rate of change or the slope, which is just interesting. So let that mull for a bit. First differences also represent the rate of change and the slope. So that M value is almost the same as first differences, and that will tell you if your relationship is linear. So the summary, the numbers in the difference column of the table of values represent the slope between consecutive points. If all of the differences are the same, there is a constant slope. This means the graph must be linear. So we'll do a couple examples here. If we sub in and solve, remember we are replacing our x in our equation with the variable, or what x is for our first coordinate. So if we say 3 times 0, that's 0, minus 1 is negative 1. 3 times 1 is 1. Sorry, 3 times 1 is 3, minus 1 is 2. 3 times 2 is 6, minus 1 is 5. 3 times 3 is 9, minus 1 is 8. 3 times 4 is 12, minus 1 is 11. And 3 times 5 is 15, minus 1 is 14. So to calculate the first differences, we take the bottom number, so 14 minus 11 gives us 3. Then here we take 11 minus 8 gives us 3. 8 minus 5 gives us 3. 5 minus 2 is 3. 2 minus negative 1 gives us 3. So this is linear. All of our first differences are the same. It is a constant slope. Therefore, the relationship must be linear. So here, negative x plus 2. So negative 1 plus 2 is 1. Negative 2 plus 2 is 0. Negative 4 plus 2 is negative 2. Negative 5 plus 2 is negative 3. Negative 6 plus 2 is negative 4. Negative 7 plus 2 is negative 5. So the first difference is 5 minus negative 4 is negative 1. 3 minus negative 3 is negative 1. 3 minus negative 2 is negative 1. Negative 2 minus 0 is negative 2. 0 minus 1 is negative 1. So looking at these, is our relationship linear? Don't say no, because something happened here. Look here. We skipped 3. So if we added 3 in here, we would say negative 3 plus 2 would give us negative 1. So in fact, this relationship is linear, paying attention to our scale. That's why scale is important. Here, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 36 squared, or 6 squared is 36. First differences. 36 minus 25 is 11. 25 minus 16 is 9. 16 minus 9 is 7. 9 minus 4 is 5. 4 minus 3 is 1. Is this linear? Answer is no. First differences are not the same, and we have a squared variable here. Lastly, we have a denominator of x. So we replace our number in the x column with that variable. So here we would have negative 1 over 2. Here we would have negative 1, undefined. Then we've got 1 over 1, 1 half, and 1/3. So for quickness, I'm going to use my calculator to subtract 1/3 from a half, and that gives me negative 1 over 6. Half minus 1 is negative 1 over 2. 1 minus nothing is undefined. Undefined minus nothing is negative 1 is undefined. And negative 1 minus negative a half gives me negative 1/2. So you can tell as we started this, this is not a linear relation. I will put up the textbook questions and possibly the worksheet for you guys to work on. If you have questions, let me know.